What's up, everybody? This is Tech G back with another video to help you successfully pass the CompTIA Security Plus 701 certification exam. So let's get into it. In this video, you are going to learn about industrial control systems, supervisory control and data acquisition, real-time operating systems, embedded systems, and high availability. All right, so let's talk about ICS and SCADA. So SCADA systems and ICSs are made up of a combination of specialized software and hardware elements that allow organizations to do the following. They can monitor equipment processes and performance. They can perform data monitoring and collection, facilitate data analysis and storage of analyzed data, perform remote control of equipment, devices, components, and processes. They can trigger alerts and alarms when performance or deviation aberrations are detected, and they can report generators for schedule and automated variance reporting and comparison, as well as production efficiency and status code statistics. SCADA systems are crucial for industrial organizations because they help to maintain efficiency, process data for smarter decisions, and communicate system issues to help mitigate downtime. The basic SCADA architecture starts with a series of configurable devices called programmable logic controllers or remote terminal units. PLCs and RTUs are microcomputers that communicate with an array of objects such as turbines, machines, gauges, sensors, and end devices, and then route the information from those devices to computers with SCADA software. The SCADA software processes, distributes, and displays the data, helping operators and other employees analyze the data and make important decisions. So, for example, a SCADA system may quickly notify an operator that a batch of products shows a high incidence of errors. The operator can pause the operation and view the SCADA system data via a human-machine interface to determine the cause of the issue. The operator can then review the data to determine whether a specific machine in the process was malfunctioning, and the SCADA system's capability to notify the operator of an issue helps that person resolve it and prevent further loss. To defend against cyber attacks, a firewall can act as a security buffer between a SCADA network and a corporate network. SCADA systems should never be connected to the internet, even with firewalls in place. You should configure internal firewalls that include VPNs for internal administration of remote SCADA systems as an added layer of protection. To address authentication and authorization security concerns, you need to configure the authentication process in the software to identify authorized users for access to the SCADA system, enable logging to track users' activity, and alerting to warn of deviations to critical controls, and ensure least privilege access. Now, depending on the perceived risk of cyber attack on the SCADA system, you should deploy intrusion detection and off-site redundancy as part of a defense in-depth strategy. So the first part will be facilities. So using facility controls like HVAC, elevator lighting, room temperature, occupancy, parking, and device usage sensors. Facility managers are able to monitor and control whether a building is operating optimally. The SCADA system can help an organization reduce its carbon footprint through energy management by automatically turning lights and air conditioning to sections of the building that are unoccupied. Next, we have industrial. So ICS and SCADA systems, they monitor, control, sense, and warn engineers of all aspects of the process in industrial plants. SCADA systems can control the flow of crude oil being turned into gasoline, asphalt, and chemicals like cleaning supplies. And such complex processes have many controls that can be dangerous if inappropriately configured. Next, we have manufacturing. So control systems in the manufacturing process depend heavily on data, performance monitoring, and capabilities to control remote equipment, which are among the most discussed concerns in manufacturing. These components are frequently mentioned as the backbone of Industry 4.0, which is the current trend of automation and data exchange in manufacturing technologies. It includes cyber physical systems, the Internet of Things, and cloud computing. Industry 4.0 creates what has been called the quote-unquote smart factory. Monitoring, data capture and analysis, and equipment control from anywhere are recognized as highly effective ways to improve facility and equipment productivity, performance, and efficiency. And the benefits of using SCADA control systems in the manufacturing process include reducing product errors and discards thanks to the earlier problem detection and remedies, improving productivity, and maximizing the effectiveness of machine uptime. Maintenance benefits of the use of data and sensors include more more accurate diagnostics, more efficient maintenance processes, and the enablement of predictive maintenance. And data-driven insights into equipment performance can facilitate more accurate calibration, operation, and decision-making processes. Next, we have energy. So the global need for cost-effective electrical power is on the rise, and SCADA systems aid in energy management. Thanks to factory automation, productivity, and accuracy, and ever-expanding data centers, there is increasing demand on electrical power utilities. An organization can integrate alternative energy uses, such as solar and wind, in its overall facility power planning to obtain efficiency, stability, and safety. For power distribution system generators, operators, and manufacturers alike, unplanned downtime is extremely costly, risky, and inconvenient. For operators, a stable, sustainable load flow across all components of a system is key for uninterrupted, safe operation. For manufacturers, any unplanned downtime can mean delays in production and missed deadlines. Predictive and proactive maintenance strategies can maximize uptime by alerting operators and manufacturers to potential issues early. In addition, transit authorities, they use SCADA technology to regulate electricity to subways, trams, and trolley buses. And also we have logistics. So SCADA systems are capable of managing parts inventory for just-in-time manufacturing, regulating industrial automation and robots, and monitoring processes and quality control. Transit authorities use SCADA technology to automate traffic signals for rail systems, to track and locate trains, trucks, and buses, and to control railroad crossing gates. Continuous communication for trucks, locomotives, and transport vehicles provides valuable information such as location and status, and is especially important for autonomous vehicles. SCADA systems can regulate traffic lights, control traffic flow, and detect out-of-order signals. Other specialized systems extend GPS and cargo tracking systems. Knowing where ships, trains, trucks, and inventory are located anywhere in the world is critical to meet today's demands for products. And these systems require special security considerations, and regulators have long insisted that these systems be air-gapped to reduce threats. A key mitigation against attacks on SCADA systems and ICS is to reduce the attack surface by segregating the SCADA network from the corporate LAN with a firewall. And ICS is managed via a SCADA system, and SCADA systems drive HMIs for operators to monitor the status of a system while in the field. And other ICS components include industrial automation and control systems, distributed control systems, programmable logic controllers, and remote terminal units. All right, moving on, let's talk about real-time operating systems, or RTOS. So in RTOS, this is a software component that rapidly switches between tasks, giving the impression that multiple programs are being executed at the same time on a single processing core. In fact, the processing core can execute only one program at any one time, and the RTS is actually rapidly switching between individual programming threads or tasks to give the impression that multiple programs are executing simultaneously. And RTOS differs from a typical operating system in that it normally provides hard real-time responses with fast, highly deterministic reactions to external events. When switching between tasks, an RTOS has to choose the most appropriate task to load next. And several scheduling algorithms are available, including round-robin, cooperative, and hybrid scheduling. However, to provide a responsive system, most RTOs use a preemptive scheduling algorithm such as VxWorks. And securing an RTOS starts with minimizing the attack surface by turning off features, services, and access that are not necessary. You should assume that external systems are insecure. Do not make assumptions about what other devices a system is connected to. It is safest to assume that external devices are insecure and approach securing them from this perspective. All right, next let's talk about embedded systems. So embedded systems are specialized computer systems designed to perform dedicated functions or tasks within a larger system. Many embedded systems have sustainable design constraints compared to desktop computing applications, and the combination of cost pressure, long life cycle, real-time requirements, reliability requirements, and lack of design culture standards can make it difficult to successfully apply traditional computer design methodologies and tools to embedded applications. Embedded systems in many cases must be optimized for life cycle and business-driven factors rather than for security and maximum computing throughput. And knowing the strengths and weaknesses of current approaches can help set expectations appropriately, identify risk areas, and suggest ways to build and meet industrial needs. All right, next let's talk about high availability. So high availability is a characteristic of a system that aims to ensure an agreed upon level of operational performance, usually uptime, for a higher than normal period. Modernization has resulted in increased reliance on these systems, which need to be available at all times. Availability refers to the ability of users to obtain a service or good or access to a system, whether to submit new work, update or alter existing work, or collect the results of previous work. And there are three principles of system design and reliability engineering that can help achieve high availability. The first one is the elimination of single points of failure. And this means adding or building redundancy into a system so that failure of a component does not mean failure crossover. Then we have reliable crossover. In redundant systems, the crossover point tends to become a single point of failure. Reliable systems must provide for reliable crossover. And then we have detection of failures as they occur. If the preceding two principles are observed, a user must never see a failure, but the maintenance activity is a must. Also, high availability is measured as the time a system is reachable. Assuming that 100% is never failing, high availability is the widely held but difficult to achieve standard of availability of a system or services known as the 5 nines, or 99.999% available. Availability percentage is measured as follows. So the formula is availability equals minutes in a month minus minutes of downtime times 100 minutes in a month. So for example, if there's a service level agreement for 5 nines, the end user can expect that the service will be unavailable for 26.3 seconds per month and 5 minutes and 15 seconds per year. All right, so that was my video where you learned about industrial control systems, supervisory control and data acquisition, real-time operating systems, embedded systems, and high availability.